in vision. So conjugated pi systems extremely important in biochemistry. So reactions that conjugated pi systems do, first are, of course, electrophilic addition, just like normal alkenes. The same reactions that alkenes do, almost completely. A couple of extra ones, like the Diels-Alder, which we'll talk about later today. So, first, I'm going to take 1,3-butadiene. Remember, I write it like this just for ease of writing it. This happens to be the S-cis, and you could write it as the S-trans, who cares? And what I'm going to do is, I'm going to add HCl, and we know how that happens, but we're going to add it, of course, as a gas, so there's no water, but I'm going to add 1 mole of each. Only 1 mole of each. So, the question is, according to our simplistic organic chemistry, is that the product? Is that the major product? Seems like that might be the major product. Markovnikov addition of HCl across the pi bond. So, what do? Well, we go back and we look at the mechanism, of course, to figure out what's happening. Okay? And I'm going to color here so we can follow what's going on. Because I know there's 2 hydrogens here already. And 2 over here. And 1 there. There. Keeping track. Okay, what's the mechanism say? Mechanism says this pi electrons are going to add to that hydrogen in a protonation process. Of course, it's reversible. First step in the mechanism is this. Intermediate carbocation. Is it stable? Is it more stable than a non-conjugated alkene would have been? Is this more stable than an isolated double bond would have been?
Yes.
Why?
There's resonance
Resonance
structures.
stabilized. That's what I want to know. So I have resonance structures, and the resonance structures are going to be this. So, resonance. I have resonance. Okay. I also have a chloride ion. And now I can see that the chloride ion could add to here, or the chloride ion could add to here. Either end is possible. So in theory, I'm going to go forward, again, equilibrium driven, and I'm going to end up with 2 possible products. Actually, 3 possible products. What's the 3rd product?
Can I get the E and C confirmation?
Absolutely. if you start from A chiral and now I've got stereochemistry, then I'm going to get both, aren't I? So I'm going to get the trans also. So I'm going to end up with both cis and trans of that form. So essentially, here's one molecule, and these two are the other product. So we actually have terms for this. We're going to say that this is 1, 2 addition, and this is 1, 4 addition. And 1, 4 addition, of course, gives me 2 possible products. Okay, 1, 2, and 1, 4. Another term that we use here is this is direct addition versus conjugate addition. Direct addition means I just added to the double bond. Bam! Conjugate addition means I added to each end of the conjugated pi system. Now we did this. People did this, and they were astounded at the results, and that's why we're talking about this. Because what they did was, they did this reaction 2 ways. First, they did this like this. They did this at minus 78, and that is called low temperature. Minus 78. Minus 78 is very low temperature, and we can easily do that in the lab. I can go down to the lab right now and get minus 78. Question is how? Dry ice. Dry ice, the temperature of dry ice is minus 78. So if you take dry ice and you put it into acetone, acetone freezing point is minus 100 and something. So you put dry ice into acetone and you can get an ice bath. Dry ice acetone ice bath, and it's minus 78. You just put your round bottom flask down into it's a liquid, it's just dry ice. You put dry ice in water, what do? Get lots of cloud and stuff, but you put dry ice in an acetone, it just sits and bubbles slowly and gets really, really, really cold. No big deal. You want lower temperature than that, use liquid nitrogen. I use gallons and gallons and gallons of liquid nitrogen because liquid nitrogen is a liquid. You just pour it out of a big thermos bottle and sits there and it's boiling, but it boils really slowly. And you put your flask down in liquid nitrogen, it's minus 100 and something, and you can do it at liquid nitrogen. But minus 78 is very standard low temperature. Easy to do in the lab. Dry ice and acetone. Every organic lab has dry ice in it. We go down once a month and get dry ice and use it. So this is dry ice acetone. And what they found was that, did I actually say no. What they found was with dry ice acetone, this is the major product, and these are minor products. The major product was direct addition at low temperature. Okay, and then they did it at room temperature, which is, in this case, high temperature, room temperature. What they found here was this was minor, and this was major. The mixture here. How to explain what happened. How to explain this difference. It's explained by energy, the energy profile. we're going to start up here, and here is our 1,3-butadiene.
Sorry, question. Why did you target 1,2 addition and 1,4 addition?
One 2 addition, 1 4 addition. But if I do 1 4 addition, I'm adding to here and here, and that will leave the residual double bond power.
Good question, all right.
Absolutely. Yeah, absolutely. You don't understand, please ask. How do I explain the difference of the two? Well, the first step, of course, is just protonation. And so we're going to do protonation, and it's going to go to this high energy intermediate cation. And there's the intermediate cation. But that's not the important part right now, in some ways. It is and it isn't. Okay. What's going to happen now is two possible things are going to happen. We have to look at the mechanism. It's all about the mechanism. So we're right here. I got this. Okay? I have this. Now, watch. What has really happened? What has really happened is that I had this right here, and I had HCl right like that. What has happened is the pi electrons added to the H, and what has happened in the very first instance is that I have that, plus the resonance structure. I'm not saying I don't know how the other resonance structure, but that's the species that I have in the solution at that moment. Notice what I'm saying. The chlorine is sitting right there. And all it has to do is add. But in order to add here, it has to come all the way around to the other side. That takes a lot more energy, doesn't it? So there's two things that are going to happen now. I'm going to add the chlorine instantly. That's low energy. Or I'm going to bring the chlorine all the way around to the other side. That's high energy. Okay? And so I have from here two processes. One's going to be a low energy process, and that's going to lead to 1,2 addition. Okay? The other is going to be a high energy process, higher energy process, and that's going to lead to 1,4 addition. This is a big deal in mechanistic theory. A big deal in mechanistic theory. You remember Hammond's postulate? This is on the order of Hammond's postulate, a complicated explanation of why things happen. So what's the point here? The first point is kinetic energy. I need kinetic energy to make stuff happen. Where is the kinetic energy involved? Right here. So I have then a certain energy of activation required to do that step. But that's easy. That's just this adding there. Kinetic energy, tiny. It's already sitting there, ready to go. Bang, makes the product. In order to make the other product, though, what do I have to do? I have to bring this chloride all the way around to the other side. And that takes a lot more kinetic energy. And that's why the other mechanistic pathway has a higher energy of activation. So, EA1,2 versus EA1,4. So, the first process in the rate determining step of the mechanism, because protonation is not the rate determining step normally, but in this case, this is the rate determining steps. I actually should say this is a little lower than those two. The reaction goes very easy. Anyway, so obviously 1,2 addition makes the easiest reaction. 1,2 addition, the fastest. It's the easiest. Least kinetic energy to do the product. And that leads to here. Okay. What's the deal about minus 78? At minus 78, the reaction is not reversible. It says the mechanism is reversible. That's what this means. The mechanism is reversible. Is that a big deal? Losing chloride and a proton, not a big deal. Because I can go back, forward, because in this case chloride is a base, because it's in the gas form, no water. So the mechanism is totally reversible in theory. Okay? At minus 78 though, it's not reversible. At minus 78, the energy of reaction of the reverse process, that EA to go back to the starting material is too high. So, at low temperature, we say that the reaction is non-reversible. At low temperature, so the reaction is over when it goes forward. It's obvious then which is the major and which is the minor product. The minor product is because the energy of activation to get to the minor product is so much higher, it's less happen. So at low temperature, direct addition is the major reaction. Because kinetic energy makes it that way. It takes energy to move that chloride all the way to the other side. So at low temperature. Now, it also says that at low temperature the reaction is non-reversible, so the 1,2 addition is fastest formed. It's the one that's formed fastest. And we have a term for that. We're going to call that the kinetic product. Kinetics. What's the word kinetics talk about? Speed. So the fastest product form is the kinetic product. Now, look at the two final products over there. The two sets of final products. Here's my two sets of final products. Two sets of final products. Who's more thermodynamically stable? This one, this set of products, or that one? The right or left? Right or left? Right. Why? Can't hear you. Less energy, but that's what lower thermodynamics means. But why does it have less energy? Why is this more thermodynamically stable than that?
The double bonds more substituted.
You got to speak up. I'm going down.
More substituted double bond.
One more time.
More substituted.
More substituents on the double bond is more thermodynamically stable. That's what you were trying to say, right? More substituents. I got two substituents on the double bond versus one. Who's that? St. Samp's rule. So, this is the more thermodynamically stable product. But it's not the major product in the low temperature reaction. But what at high temperature? What's happening at high temperature? The mechanism is the same mechanism, but the product distribution reverses. What does that say? At high temperature, the reaction is reversible. And this is a huge point that we will look at least 5-10 more times this semester. Reversible versus non-reversibility. Major point. Reaction's reversible. Well, wait a second. I've already pointed out this is more thermodynamically stable than this, because that's why this is lower energy than that. This is more thermodynamically stable. It's lower in energy. What does reversibility require now? Reversibility, though, requires this energy of activation, but it also requires this energy of activation to go back to the original cation intermediate. So, energy of activation for the two reversible processes. Now we're at high temperature. Now there's plenty of energy to do anything. Both processes are now reversible. Both processes are reversible. Okay, so watch. I'm going to start with 10 of these at high temperature. 10 of these at high temperature. What is this? This is the fastest formed. That's what it says. This is the kinetic product, so it's the fastest. This product is formed the fastest. So I start with 10 of these, and in 5 minutes, I've got 9 of these and 1 of these. But I don't just wait 5 minutes. I stir this for 2 hours. What's going to happen during the 2 hours? During the 2 hours, it's going to be, we're never going back here. It's just going to go back and forth, back and forth, back and forth, back and forth. Think about it. I got 1 of these and 9 of these. Of the 9 here, all can easily get back to here. Of the 1 here, it eventually can get back there. Difference in energy of activation. But when it comes back, now there's going to be 8 of these and 2 of these. All 8 of these can go back. When these come down here, only 1 of the 2 can get back because the energy of activation is so much higher. So after a half hour, now I've got 7 of these and 3 of these. After 2 hours, I got 1 of these and 9 of these. Reversibility. Think about the old idea of a frog falls into a well. How does it get out? Jumps up, falls back, jumps up, falls back. So, everything's falling over here first, but it's back and forth, back and forth, back and forth. But when I'm down here, I can't get back as easily. So not everybody here goes back to there as easily as here. So in the first 10, 15, 20 minutes of the reaction, it's almost all this and then this. Very tiny. But we don't do that. We don't stop it. We let it run because we want what's now going to be called the thermodynamic product. So what that says now is that 1,4 addition is the major product due to reversibility. Leading to what we are now going to call the thermodynamic product. Why do we stir reactions sometimes 1, 2, 3, 4 hours, maybe a day? We want to get the main product that we're going to get in the reaction. And sometimes because the process is like that, the initial process leads to a kinetic product, which is not really what we want. And all we got to do is be patient, and we'll get the main product being the thermodynamic product. What's the whole deal? Why is it going this way? It's right here. It's all about kinetics. If I'm at low temperature, hydrogen adds, and the chloride's sitting there, and it's cold, and it's shivering, it doesn't have enough energy to move to the other end of the double bond system, so it just adds. But at high temperature, what happens? I get enough energy, I can move it anywhere. No big deal. But, again, the initial product is still going to be the direct addition, the 1-2 addition. Over time, thermodynamics gives us the major product. Everybody understand? Now, one last little point. Well, not one. I've got one more point. Why is that a squiggly line? We do that in the book. We do that in organic chemistry. Why is this a straight line and that's a squiggly line?
Not stable.
I can't hear.
Not as stable.
No? The product has the chloride on there. If I start from a chiral starting material, is this chiral? Yeah. If you start from a chiral starting material, but you make chiral products, what do you end up with? And that's how we show that by the squiggly line, means that I made both. That's our shorthand notation for organic chemistry, meaning I made both isomers. Now you're not going to do that on the exam, but you see this in books, very commonly in books. They'll put a squiggly line, meaning they made the 2 stereoisomers of that stereocenter. Everybody see it? Okay? They figured that out. Sounded cool. So they tried out other things. Let's see if we can do other reactions, and it's going to give us a similar process.
So it's safe to say that time plays a big role in making thermodynamic products. I'm saying it's safe to say that time plays a big role in making it.
In some reactions, time plays a very big role. In this, time plays the role in deciding which is the major product. Absolutely. Absolutely. Okay. Show me the products, first of all. Show me the products and then tell me which is the major product. Oh, I forgot.
Is there any other reason that you write low temperature other than to indicate that it's non-reversible?
Yes, that's the reason.
That's the only reason.
That's the only reason in this case, that's the only reason.
So it should be 1, 2.
I'm sorry?
1, 2 is probably the major product in this one.
Must be a reason I'm asking this question. Did you work out the mechanism? Did you work out the mechanism? This is not just look at it. You have to know the mechanism. Why did 1, 2 versus 1, 4 happen in the previous reaction? And how does that concept impinge this concept of this reaction? What's the mechanism? Come on. What's the mechanism? What's the first step?
Like a pericyclic, the Br.
So, pair of electrons adds to bromine and that goes away, correct? And we end up with the bromonium ion plus the R minus. Correct? Correct so far? Okay? Explain it. Explain it to me. I'm going to give you the answer. Now you explain it to me.
Less is correct. The major one is less is correct.
Why? This has nothing to do with thermodynamics. Has nothing to do with thermodynamics.
Like bromination?
The bond, the bond on the far end can add and shift over faster than the Br minus can come in and hit it.
Wait a second. Say it again.
If so, there's a delta positive on the Br. So if the double
This is a positive charge because it's in a bromonium.
full
ion.
positive,
But it has resonance, doesn't it?
there's a resonance structure.
There's resonance structures here. In fact, there's more than 2 more resonance structures, right?
Mm-hmm.
Because once I put the bromine over here and the cations here, then I can put the cation over there, can't I?
Mm-hmm.
So there's 4 or 5 different resonance structures. I'm not just saying no. There are other resonance structures.
Okay.
That's not the point. What was the deciding point in the first reaction? Why was 1, 2 faster than 1, 4 in the first reaction that we looked at with HCl?
The energy it takes for the.
To do what?
Location of the chloride.
Exactly. Kinetic energy. In the first reactions, what happened? The H and the Cl. I add the H, and the Cl is sitting right there with that cation, and it doesn't have to have any kinetic energy to add, does it? So, extremely low temperature, it goes instantly because it's already sitting there. But in order to make 1, 4, I have to have kinetic energy and move the chloride all the way to the other side, don't I? Yes? How does that have anything to do with here? What's the next step in this mechanism? The bromide ion is going to add, isn't it? And this bromide ion is going to add one of 2 places. It's going to add here, or it's going to add there. Why isn't it going to add here?
Does it take more kinetic energy to move?
Because the positive charge here is the primary positive charge. Because if I have that cation, that's more stable than that cation, right? Because there's 3 resonance structures right here. And so the main second resonance structure is going to have the positive charge here. So that's why the bromide adds there instead of here. But anyway, what's the mechanism? What's the stereochemistry of the mechanism? Anti-addition. What does that mean? This bromine is sitting right here, but the other bromine's right there. In order for this bromide to react with that carbon, it has to come all the way around to the other side of the molecule, doesn't it? Anti-addition of bromonium ions. Well, coming all the way around to the other side to add here versus coming all the way to the other side to add there, it's the same essential kinetic energy. A flat double bond. I've got a bromonium ion right here. The other bromide's sitting right here. It has to come all the way around to the other side to add here. It has to come all the way around to the other side to add to the other end too. So the kinetic energy to come all the way around to the other end here versus there, the kinetic energy is essentially the same. So the main product is the thermodynamic product. Because addition of that second bromonium, the second bromide to the bromonium ion has the same kinetic energy because it is anti-addition. So this, in some ways, proves our first concept. Essentially the same basic reaction, but this one leads, this is the major product. Thermodynamics is the major deal there. Because the energy of activation forward and backwards, the energy of activation forward is the same to add here or to here. Essentially the same, so thermodynamics controls the final product. Awesome.
On the 1,4 products, does it still add anti even though they're not on adjacent carbons?
How do you know? How would you know? Are the two atoms where I'm adding the bromine chiral? You see my point? There's no stereochemistry
Right,
here.
so it doesn't matter.
And there's no stereochemistry here. So when I'm at this point and this bromine is coming in from the top face or underneath from the bottom face, how do you know? That's a question. We don't have the answer to that question because we can't see it. There's no evidence of it. You see it? Very perceptive question, but it doesn't matter because they're both going to lead to the same product. I have an old organic professor. I took organic 1 year at University of Pacific. I wanted to go to the West Coast to get a PhD, and so I applied to 10 schools on the West Coast, 14 schools, and 10 of them accepted me, and I wanted to be as close to the Bay Area as I could, so I went to UOP over in Stockton. But they have a terrible chemistry program. At the time, their facilities were horrible. And so after a year, I transferred to Mad Reno, which has fabulous facilities, and that's where I got my PhD. But while I was at UOP, one of the organic professors I had, Paul Gross, he was a German. He looked just like some Nazi bald head right out of the spoke with a German accent, and he taught me all of this stuff because Zabromonium ion, you have to talk about Zabromonium ion. But he'd always go, how do you know which way it went? You can't see electrons. How do you know which way the electrons went? Who cares? So it's not an important point here because it's coming around from this side or coming around from the back side. It's not leading to stereochemistry, so who cares? So, thermodynamic versus kinetic. You will reproduce this whole argument on an exam or a quiz soon. This whole energy level profile, you will show me that on an exam or a quiz in the future.
Is that from anti-addition always in low temperature only, or
Which anti-addition?
the anti-addition of the bromonium?
What do you mean?
Well, the reaction.
Bromine addition to alkenes is always anti-addition, isn't it?
Yeah.
What's your question?
My question is, does temperature affect the reaction?
It doesn't in this case because it always, if I'm adding 1,2, it has to be anti-addition. But if adding 1,4, anti or syn, it doesn't matter because I'm going all the way to the other end anyway, and it's flat over there, so who cares? That's the point.
So
Okay.
the major product is it's the kinetic and the thermodynamic product.
In bromination, the thermodynamic product is the major product.
Okay.
That's what I said. The 1,4 addition is the major product in bromination.
Okay.
Because 1,2 because thermodynamics versus kinetics. In this case, kinetics has nothing to do with it. It's thermodynamics. Okay. Okay. Next reaction is a reaction we're going to do in a week or so in the lab. We're going to do it a week from Tuesday. This is called the Diels-Alder reaction. Diels-Alder reaction. This is a very interesting reaction. I love this reaction. Diels-Alder reaction. Otto Diels was a Danish chemist. Kurt Alder was an English chemist, and they both worked together in their respective countries, but they worked together on the same process, on the same product, and same reaction and everything, and so they talked to each other every day by phone and so on. This is back before World War, and during, actually before World War II. They won the Nobel Prize for this in 1950, for this specific reaction. That's how important this reaction is, even to this day. Diels-Alder reaction. Okay. Now, the essence of the Diels-Alder reaction is we're going to take an alkene, and we're going to add a diene. Now, notice I wrote the diene as the S-cis form. Of course, it rotates at all times in solution. The S-trans form is the major form. The S-cis is less. So there's never more than like 5 to 10% of this in the solution at any one time. But because of room temperature, there is an equilibrium, and it's always going to have 5 to 10% at least of the S-cis. And as the S-cis reacts, then the residual starting material continues to isomerize, and eventually the whole reaction goes forward. Now, what we're going to do is we're going to take this and we're going to heat it up. That's it. All we're going to do is take those two compounds and heat them up. The product red here. The product is this. Diels-Alder reactions make rings. Diels-Alder reactions make rings. Now, we're going to call this a 4+2 cycle addition. A 4+2 cycle addition. And it's one of a series of reactions called electrocyclic reactions. This is just one of them. We're going to look at a whole bunch of these. They're all governed by specific rules. The rules were developed, as we'll see, by two professors, Woodward and Hoffman. R.B. Woodward, the greatest organic chemist of the 20th century. My PhD advisor's PhD advisor. He was a professor at Harvard, won the Nobel Prize, truly the greatest organic chemist of the 20th century. Hoffman was a junior professor at Columbia at the time, Roald Hoffman, and they worked together. Woodward was the big cheese, and Hoffman was this little junior guy, but they were both interested in electrochemistry, and they both saw the Diels-Alder reactions and a whole series of other reactions, and they put together the whole theory that governs all of these, and the theory is electrocyclic reactions, and we'll look at them at the end of the discussion of the Diels-Alder reaction. So, this is what's happening. Now, watch. You want to memorize this reaction. Here's how you memorize the reaction. You got to watch. To memorize the reaction, this pi electrons, and that pi electrons are all getting together. There's a p orbital, p, and this p orbital is going to react with that one, and this p orbital is going to react with that one, and the two resulting p orbitals are that double bond right there. Now, simplistic view. You want to just memorize and be stupid? That's what we are looking at in terms of simplistic view. That's not what's happening. But if you just want to look at the carbon structure and how to look at the final product, that's how I figured out the final product. Just take this bond and put it there, and that bond and put it there, and that double bond. That's not the actual reaction. Okay. So, This turns out to be, of course, another definition, a pericyclic reaction. What does it mean?
Goes to a cyclic transition state.
Cyclic transition state, A for 10. Cyclic transition state. Now, what that means is, while these two are reacting, it seems that what we're doing is we are now making this bond, and making that bond. We are breaking this bond, and that bond, and that bond. So bond breaking, bond making, and there's my double dagger transition state. So the red bonds are being made, the purple bonds are being broken. A cyclic transition state. Now, this is called the diene, and we're going to change the name of this, and we're going to call it the dienophile. So there's the dienophile. What does phile mean?
Loving.
Loving. So this is the diene loving. The diene and the dienophile. Now, Gilson Alder did this reaction a whole bunch of different times. This was the first reaction they did. And they started putting substituents all over it and saw what happened. And they found that if the dienophile, let me put it in a different color, is electron poor, and the diene is electron rich, the reaction is faster. They found that if the diene is electron rich and the dienophile is electron poor, the reaction goes faster. Okay. What's electron poor mean? It means it has functional groups that suck electrons. What are substances, atoms, functional groups that suck electrons? Carbonyls. Carbonyls have very electropositive carbon. So carbonyls suck electron density. We call them electron withdrawing groups. Right? What's another one? C triple bond N. Again. Nitriles. Electron withdrawing groups, we call these. Much stronger than just the simple dipole of a fluorine or a chlorine. By far stronger than the, polarizability of bromine and iodine. So these are our strong electron withdrawing groups, and we're going to use these as electron withdrawing groups through the whole rest of the semester. So if I put either of these on something, they're going to be sucking electron density out of that because of their polarity. What about electron rich? Electron rich, those sort of things, they're going to be R, and another one of the electron rich, of course, is OA, where A is hydrogen, carbon, something like that. Why is R an electron donator? How does R group donate electron density?
Induction.
I'm sorry?
Induction.
Induction. Hyperconjugation and inductive effect. R groups. Weak electron donators. How about the other group? These are alcohols, ethers, esters. How are those electron donators?
Resonance.
Resonance. Remember this one right here? Go back, last semester we looked at this. didn't we? Why is that such a powerful nucleophile? Because the oxygen here is donating electron density by resonance over to here. So ethers and alcohols pull electron density by inductive effect, but they donate by resonance. And so in this case, those things, alcohols and ethers and carboxylic esters, they're going to donate electron density by resonance. And resonance always wins over inductive effect. So if you're pulling by inductive and donating by resonance, resonance always wins. So that's why that is a donating group. So what Diels and Alder did was they looked at some of these reactions, and here's one that they looked at. I have these aldehydes. By definition, you just heat them up. I want to write the product, and I can do that already because I memorized the simplistic view of how the reaction is going to go. I didn't memorize the mechanism, I don't know it for sure yet, but I memorized the simplistic view, and what was the simplistic view? Right here. Right there, and there's my simplistic view that'll help me get the product. What am I going to do? I'm going to take the end of this and attach it here, and the end of this and attach it there. The two ends of the pi system bond together. So, essentially, remember, this is not the mechanism, and then that goes there. So this is not the real mechanism. This is just our simplistic view to try and figure out the product, and at least get half the points in the question because I forgot the mechanism. I can still get the product with this, but I can't explain why and how. So, I have one ring. What do Diels-Alder reactions make? A ring. So I'm going to end up with bicyclo compound now. So those of you from last semester, I know you can do it, but everybody, you got to now figure out how to do bicyclo compound. Okay? So here we go. There's my two pieces that I have now put together. I put them this way just because it's easy. I could have done it the other way around. I could have come over here and done this one the way I've got it lined up over there. Either way, they're both the same product. Depends on whether this was over there or this was over there, however you want to write it. Okay? Now, the stereochemistry of the two aldehydes. The stereochemistry of the two aldehydes were they were cis, and they maintain their stereochemistry over here. They maintain their stereochemistry. And the stereochemistry here is going to, I should have done a different one, but that's okay. They maintain their stereochemistry. And also, now, there's the second double bond, or the residual double bond. Okay. They're the same. Same compass. Is it chiral? Hands up. No. Plane of symmetry right through it. Achiral, achiral, achiral. Now, what do I notice? An important point here, nitpicky point, is where are the aldehydes in relationship to the residual double bond? Where are the aldehydes in relationship to the residual double bond? This is a big deal. Notice where they are. Notice that the aldehydes are close to the residual double bond. They're not up closer to the alkane. Must be some stereochemistry going on here. Must be some stereochemistry going on here. So, first of all, we have a word for this. And we say that this is the endo rule. Diels-Alder follows the endo rule. So, endo. Endo talks about bicyclic compounds and their stereochemistry. Okay. Endo. Endo says that what we're talking about is trans, the substance that's endo, is trans to the less complicated or smaller bridge. It's trans to the less complicated or smaller bridge. Okay? So here we go. Watch. I'm going to be standing right here. First, I'm going to start right there, and I want to know which of these two is exo and which one is endo. So, if I'm standing here and I look down, which is the less complicated bridge? This one. 2 carbons versus 1 carbon. So, the endo substance, this one or that one, is trans to this. Okay, what does that mean? Well, look. That's trans, isn't it? But, notice, this is cis, this is trans. So this must be endo, and this is exo. So exo is cis to the less complicated bridge. And here we are, here's exo. Exo is cis to the less complicated bridge. But we're endo. Okay? So that was for that position. Let's move down here now. Which of these two is exo and which one of these two is endo? Well, if I'm standing here, where's the less complicated bridge? Up here. Which of these two is trans to this? I'm going here. Up, up, up. Trans. So this must be endo, and this is exo. Because look, less complicated bridge, exo, cis. Cis, trans. Everybody with me? Okay, the final one here. Which one is exo, which one is endo? Less complicated bridge, up, trans. So this must be endo, and here's exo. Everybody understand exo and endo now?
So the less complicated bridge is
Means
means
right here. Because over here, both of these are 2 carbon bridges.
Mhm.
But this is less complicated because it doesn't have the double bond. Okay? Look at the substituents here. Where are they? Trans to the less complicated bridge.
Okay.
Endo. And that's why the aldehydes are down. Excuse me. The fact that they are endo is because the aldehydes are down. Now comes the question of why did this happen? Why did this happen? Okay. It has to do with this mechanism. Here we go. Both of these compounds are flat. They're both flat. What I have is p orbital, p orbital, p orbital, p orbital, p orbital, and p orbital. So in order for this to happen, what's going to happen? Look at it. What's happening is this p orbital is reacting with this p orbital to make the new sigma bond. This p orbital is reacting with this p orbital to make the new sigma bond. And the 2 p orbitals here are the resulting final leftover double bond. What does that mean? Here's the 2 molecules. But remember, they're both flat. Okay? They're both flat. And they've got p orbitals. P orbitals. And p orbitals. 1, 4. 1, 4. 1, 2. They have to come together. The p orbitals come together like this. What that means is the face of the 2 molecules must come together. So they have the 2 faces come together. Okay? So let me draw it for you on the board and you'll see more easily what I'm talking about. Okay. I'll draw it over here according to this right here. So, what I'm going to have now is better one. Okay. Let me put in their p orbitals. Okay. Now, the aldehyde has to be underneath this. The aldehyde has to be underneath that. Now, what? The aldehyde has to be flipped over. So it has to be like this. And those p orbitals. Okay? They must have this stereochemistry to do the reaction. Very well. I didn't say this. I misspoke. The fastest way to do the reaction, the lowest energy of activation for the reaction is this configuration. Now, what's happening here is, look at this grid. So, what's happening is this electron and that electron are getting together. This electron and this electron are getting together. That's forming this new sigma bond. Okay? Those 2 interactions are forming the new sigma bond. we go. The aldehydes are out there. Aldehydes are there. This is the double bond, and here's my butadiene. So what am I doing? I'm adding like this. I'm adding like that. Okay? Adding like that. You see it? Adding like that. Now the question is, wait a second. Why couldn't I add it like that? Why can't I just turn this around and do the same reaction? Why does it have to have the aldehydes facing? Looks like it's a little more sterically crowded. But that's the mechanism. The reason why is it's well known now that that's what the electron withdrawing groups are. These have p orbitals too. And these p orbitals interact at the transition state with these interior p orbitals. And that stabilizes the transition state. So, the withdrawing group p orbitals interact with the residue double bond p orbitals, stabilizing the transition state. It only stabilizes the transition state. There's no chemical reaction. The interaction stabilizes the transition state, and that gives a lower energy transition state than the opposite, than the other stereochemistry. And that's why by far the major product is the endo product. By far the major product is the endo product.
So only electron withdrawing groups with p orbitals do this, not like fluorine or iodine and all
Nope,
these stuff.
nope, they're not strong enough to make it, force it to go endo. Yes. Carbonyls and nitriles. Those are the electron withdrawing groups that we use. Now, I have to remember, and you have to remember also, what are we doing? We're trying to make organic molecules. And we're not putting fluorine on organic molecules, except for rare drugs. Because fluorine doesn't do any chemistry. I got pointed out last semester. I finally realized there's a lot of fluorine on a lot of drugs. And so I went to one of my pharmacists and I go, what's this fluorine all on these compounds? Fluorine is the second strongest bond in chemistry. Fluorine never does anything. He says, yeah, but fluorine is extremely electronegative and it hydrogen bonds better than water does. And so what it does is it attracts water to the molecule and makes it more water soluble. So fluorine on a drug just makes the drug more water soluble because it attracts water much more strongly. The reason for fluorine. So it points out then, if I turn this around, I don't have this interaction. It leads to the exo product, but that's a minor product because that has a higher thermodynamic or higher energy of activation. Okay, Austin. Okay. Transition state. You know what transition state means? If you don't understand something from last semester, you got new guys or whatever, you don't understand what I mean by transition state, you got to let me know. Because what does it mean? What is transition state? Nope. What is by definition? It's a state. But what is that state? That transition state?
Bonds being made and broken.
It's the point where the bond energy of bonds broken equals the bond of bonds made. Transition state says that bonds here are halfway or approximately, and bonds, so halfway they're made here, maybe not, depends. We looked at this with Hammond's postulate last semester. Transition state is the break-even point. So I got to put energy in to get to the highest energy point. From then on, it's downhill. So that high energy point is the transition state. It is the highest energy point of the whole reaction. So there we go, and there's the reaction. Awesome.
So why, I'm not getting, why is it that if you rotate the bottom molecule, you don't get the same type of interaction?
If I turn this around, now I'll have this. And now this orbital and that orbital are reacting here and here. And how are these involved with that? These are sticking out that way, and these are way over on the other side.
Oh.
Remember, you have to remember the mechanism. They're coming in face to face. And so turning it around face to face just points the carbonyls the other way, and they can't interact with the... So what's happening here? Here's my double bond, right there. Here's my alkene with the carbonyls at this end. So now that's the bond forming, but the resulting double bond is here, and the carbonyls are here, and they're interacting at the transition state. If I turn this around, they're not interacting at the transition state. There's no stability. Get it? All right.
At the transition state, the p orbital 1 and 5, are those carbons experiencing like a delta positive?
There is no delta positive or delta negative. This is totally neutral reaction. There is no polarity in this reaction. This is just a p orbital coming together, like a radical reaction almost, to make a sigma bond. So the two p orbitals come together to make a sigma bond. And this electron and that electron now become that sigma bond right there. That sigma bond right there. So here we come. P orbitals just become a sigma bond. Okay?
So,
James.
do the electron withdrawing double bond groups that stabilize this reaction, do they have to be bonded directly to the
Diene or the
Diene.
dienophile, yes.
They have to be
Every-
close,
look.
otherwise it won't work.
If I put this carbonyl 6 carbons away, does it do any good?
No.
It has to be exactly on the dienophile. Okay? Everybody with me so far? Okay. Explain this using molecular orbital theory. Explain this using molecular orbital theory. Why does this reaction work, and why do electron withdrawing groups and donating groups make it go faster? Why is it that withdrawing groups here and donating groups here, what's the donating group here? This carbon. These are alkanes. These alkanes are donating into the pi system. This is electron rich, this is electron poor. Diels-Alder said that works best. Question is why? Well, 30 years later, other people were playing around and they said, wait a second. Diels-Alder said electron withdrawing groups and electron donating groups. What happens if we turn it around? What if we put electron donating groups here and electron withdrawing groups here? This was 20, 30 years after Diels-Alder, because they were too busy making new molecules by putting an aldehyde here, a chlorine here, an ester here, and so on. They were just doing their reaction. And somebody else says, hey, let's turn their reaction the other way. Let's see what happens. They turned around the other way, and guess what? Still works. Still works. How's that happen? So what are the electron withdrawing groups and donating groups doing? Okay. Why did I make you go and do the molecular orbitals? So that you understand this. So here we go. I've got two sets of molecular orbital theories right there. What have I got? Put in the diene. No, put in the diene first. Put in the dienophile. Go ahead and finish it. Color it in. Put in the electrons. right here. Okay. How much is the video, James?
Hour and 16.
I'm sorry?
Hour and 16 minutes.
No, I'm asking how much you're charging the rest of the students for. 10 years ago, I had a student videotape it. They actually, back then, they didn't have those things. Set up a videotape in the back of the classroom every single day. I got the DVDs in my office. I went to put them on the net, and I said, our storage capacity isn't big enough for 2 semesters of organic chemistry, forget it. But now it is, and so hopefully by the end of this year, I'll have all my lectures put on the web. But, and you'll see this exact lecture. You gotta be able to do that by the first quiz. When's the first quiz? Next week. Let's see here. Quiz 1, a week from today. So everything in today could and will be on the quiz. Okay, you ready? Molecular orbital theory. There it is. HOMO, LUMO. What are we doing here? What we're doing, according to Diels-Alder, is we're taking these pi electrons and they're promoting them over to react with that. What that says mechanistically, according to this, is I'm taking electrons from one place and putting it into another. And traditionally, what's going to happen is the HOMO electrons go into the LUMO of the other molecule. The HOMO electrons go in the LUMO of the other molecule. Logic? What are HOMO electrons? Nucleophiles. What are LUMO orbitals? Empty orbitals, electrophiles. So, I'm going to now take my HOMO electrons and put them in my LUMO of the other molecule. That's the first step. That's all we know. That's the first step. Okay? Now, look here. I've drawn this in a specific way. Remember, I pointed out that the center line here is lower than the center line here, meaning that this is more thermodynamically stable than that. I also point out that this delta E is smaller than this delta E. Conjugation means more thermodynamically stable. So, the HOMO-LUMO gap, non-conjugated, is much larger than the HOMO-LUMO gap conjugated. What does that mean? Conjugated is more reactive. It's easier to put these electrons up there. Unconjugated is less reactive. More thermodynamically stable, but more reactive. Less thermodynamically stable, but less reactive. So, I notice that I want to put the HOMO electrons into the LUMO. Which way is it going to go easiest? Which HOMO electrons are going to go easier into a LUMO electron than the other one? I can take these HOMO electrons and put them up there. Or I can take these HOMO electrons and put them up there. Which one's smaller?
Isn't that the same?
Is this distance the same as this distance? Is this distance the same as this distance? I'm putting these here or these all the way up there. They're not the same distance.
Yeah, almost was.
This is a smaller distance, isn't it?
Yeah.
Okay, so I'm gonna take those electrons and put them up there. That's the way the reaction wants to go, lowest energy. Everybody see it? So my question that I'm trying to answer is, what is it with these electron withdrawing groups and donating groups? What's happening with them? What's an electron withdrawing group going to do? So we're looking at this right here. Here's my alkene, and there's its thermodynamic stability. What's going to happen if I put an aldehyde on here in the withdrawing group? What's going to happen to the energy of this system? Is it going to go up or down? I'm sucking electron density out of it with an electron withdrawing group. Does that make it more stable or less stable? Fourth semester chemistry. I'm sucking electron density out of something. Does that make it more like a noble gas or less like a noble gas? Should I just leave? You're not going to answer questions. You're not paying attention. Somebody's got to say something. I'm not going any further. All of you are smarter than me. You know what's happening. Please answer my question.
What is it?
Sucking electron density, does that make it more stable or less stable? Less
Which one?
stable.
Less.
Does it make it more like a noble gas or less like a noble gas? Less. So sucking electron density out of here, what does it do? It raises this whole thing, doesn't it? So pumping electrons into this side, what does that do? It lowers the energy of this whole thing, doesn't it? What does that do to the HOMO-LUMO gap here?
Lowers
If
it.
this goes up and this comes down, it makes the HOMO-LUMO gap get even closer, doesn't it? Electron withdrawing groups make this go up to here. Electron donating groups make this LUMO come down to here. Now they're really close, and now the reaction goes super fast. So, molecular orbital theory proved what Diels and Alder saw by experiment, that putting electron withdrawing groups on the dienophile makes the reaction go faster, because it raises the HOMO of the dienophile. So, electron withdrawing groups raise the HOMO. Electron donating lowers the LUMO, and therefore the HOMO to LUMO gap is smaller, so therefore less delta E reaction, less energy of activation required. Molecular orbital theory. It proved what we saw by experiment. Molecular orbital theory, that's why I had you draw this. More thermodynamically stable but more reactive. Less thermodynamically stable but less reactive. But yet, here's my HOMO, here's my LUMO. If I raise this, lower this, these two get closer together, the reaction works beautifully. Now, I said that 20 years later, other people turned it around and found it worked also. Why? What's the reverse? If I put electron withdrawing groups here and donating groups here, now which way does the mechanism go though? Does it still go the same way?
It goes the other way. This is gonna
And that, if I raise this and lower this, now these electrons are going to go into there. It still works the same. So, electron donating, withdrawing groups. They raise and lower, make the reactants get closer together in energy, make the reaction go faster. So the Diels-Alder reaction shows that. Electron withdrawing groups on the on the dienophile, and donating groups on the diene make it go faster, or the reverse. Major big deal. We're going to do this reaction in the lab in a week from today. A week from today, I think. Diels-Alder. What we're going to do is, I'm gonna give you two compounds like this, and you're gonna make this compound, and you're gonna take the product, and you're gonna do a chemical reaction and get a product, and I'm gonna tell you what it is, and then you're gonna take that product and do another chemical reaction, and you've gotta figure out what the product is by mechanism. Nice puzzle. Huge amount of stuff today. Major day. What do we start talking about? Kinetic versus thermodynamics. 1-4 versus 1-2 addition. Direct addition versus conjugate addition. Major concept. This, completely different concept. Molecular orbital theory to explain Diels-Alder. Those two processes are two very important processes that we'll talk about the rest of the semester. And so for the whole semester, both of today's talks are very, very important for today's whole semester. We're going to look more at other reactions like Diels-Alder. We've seen one. You saw them last semester. One of the reactions was
analysis. Analysis.
Analysis. This is not the mechanism. Just like I showed you, that's not the mechanism. This is the easy way to figure things out. Monoazonide. What's happening? P orbital, P orbital, P orbital, P orbital. Essentially the same basic mechanism. You just didn't know it because I couldn't explain it to you last semester. It was an opposite. Same basic mechanism. I'll talk about it next time. That's all for right now. Questions?